Okay, so let's take a look again at Gauss's law and look at some more examples of using it to find the E field. To begin with, we're going to look at spherical symmetry, and I want to look at what we call the symmetry arguments, which allows Gauss's law to be made much simpler in terms of applying it. So we're going to take a 3D charge density which only depends on the radius. Let's consider this rho of r to be a sphere of charge that extends to some radius capital R, shown here, and has a value that drops to 0 once we reach the edge of the sphere. So for r equal to or greater than r, we have 0 charge density. So what we're going to do is take the point P along the z-axis. So we orient the sphere such that the z-axis is shown here and the point that we're interested in is shown here. Okay, so we'll also let that distance be little r from the origin. So sometimes I'll say r, sometimes I'll say z for the position of this point. To start with the symmetry arguments, we're going to try to show that the E field here is in the same direction as the vector z hat or r hat. To do that, we first select a ring of charge inside the sphere, and we'll let it be a radius s, and we'll let it be located at some distance a from the origin. And you can see how it's oriented with respect to the z-axis. Because these points are equidistant from the origin, the ring has a constant effective lambda. And remember that if you take a 3D dimension and change it to a 2D dimension, it's a very simple step in terms of finding lambda from the 3D charge density. To make it clear, this would have to have a width, which you could call dA if you wish. We know from earlier derivations that dE, due to this ring of charge along the symmetry axis, depends only on z, which means it only depends on r. So in other words, the vector E can be written as a function of r only. We also know that the E field is in the z direction, and therefore in the r direction. So we can come to the conclusion that the dE, due to this ring of charge, is equal to the magnitude of dE, which is a function of r, and points in the r hat direction. So what we're talking about here is a dE that is due to this particular ring of charge. This is just to repeat what I've said so far. To get the total E, we have to integrate over the sphere of charge. And we can do that by using these rings and simply let the ring cover all of the inside of this sphere by changing A and by changing S. So you can imagine tons of rings that are sweeping out this volume. They all have this same orientation relative to the point P. So if we take all of those dEs and add them up, then we find that E then is just like the dE from a single ring. It will be in the r hat direction, and the magnitude will only depend on the distance r. This is a very important result for using Gauss's law. It's important to realize that this is what we mean by a full symmetry argument that then allows us to find E using Gauss's law. There are two extensions of these arguments. The first one is that it also holds inside. So if you take a point inside, you can make the same arguments that I showed you here, and you will still come up with the same results. Secondly, it holds even if this function rho of r does not terminate. So in other words, if it has a dependence which continues to exist out here, then it will still hold. So in other words, it would be like being inside this particular charge distribution, whereas you're outside, but you still have some charge density that are giving you this result. But realize it has to be a charge density which only depends on r in order to apply these particular results. Well, I just wanted to give you an example. We're not going to do it right now, but just imagine that you have a charge density which is like an exponential of minus alpha r squared. This is called a Gaussian function, by the way. Has nothing to do with Gauss's law, at least not to my knowledge. And this extends to infinity. It gets very, very small as r gets very large, but it still exists. It does not terminate. You can find E of r then at any r by taking advantage of this result. It occurs because rho of r is a function of r only. And by saying we find E sub r, it means that we're going to use Gauss's law. Well, let's consider a problem. This is a sphere of uniform charge, and we'll say that it's a capital Q charge and it's uniformly distributed through this sphere of radius a. And what we're defined is E everywhere, which means inside and out. We can calculate the charge distribution for this function by just simply relating the Q and the volume. If we're inside, we have the charge over the volume, which is Q over 4/3 pi a cubed. If we're outside, because it terminates, we get 0. So this particular charge density is resulting from having a constant rho inside. And realize that this is a constant, and by this arrow I mean this whole thing. Secondly, because of spherical symmetry, we've got the form of the E field by the symmetry arguments that I just gave you, and we'll assume that it's true both inside and out. So let's first look at points that are outside of this sphere. So what we're going to do is draw a Gaussian surface at this radius r. It's a sphere surrounding the sphere of charge. We're going to find the E field on this surface. The flux passing through the surface S, we'll call phi sub s, is equal to the left-hand side of Gauss's law. The right-hand side, of course, is over here. For this S, our symmetry arguments allow us to write that E is equal to E sub r, r hat. For a given r, it's constant, and it's in the r hat direction. What about ds? Well, ds will be some area ds, a scalar, times r hat. When we write E dot ds, we put in our E right here, we put our ds vector here, and we've got r hat dot r hat, which is equal to 1. So we're left then with scalars, E of r, which is constant on the surface for a constant r, times ds. So rewriting that then, we'll have the integral, the flux integral here, is equal to, now this is a constant on that surface, so we can bring it outside the integral. So we have E sub r times the integral of ds over s. Well, that's just the area of a sphere. And since the radius is little r, then that's the area of a sphere, radius r, which you know is 4 pi r squared. Now what about the right-hand side? We've already said that the Q enclosed is equal to the total charge here, and that was given in the first of the problem. And that's just equal to Q. So if we put Q in for the Q enclosed and divide by epsilon 0, we have the right-hand side. Equating the left-hand side with the right-hand side, we can solve for E sub r, and so we end up with Q over 4 pi epsilon naught r squared. Changing this to a k just to put it in a form that might be more familiar, what we see then is that the E sub r is equal to the magnitude of E sub r times r hat. Well, this is exactly the same thing as a point charge, and the point charge would be at the origin. To finally get this result, I want to make sure you understand that first we had to make the symmetry arguments, and then we had to use the symmetry in order to evaluate this integral here. The integral gave us a scalar E sub r, the E field as a function of r, times the area of the sphere. So we have the left-hand side in a form that if we find the Q enclosed, we're able to solve for the magnitude of E, and we've already said that it's in the r direction, so this is the result. So let's go inside. So now we have to draw a Gaussian surface inside. We say that it's a function of r again. So we wish to find the E field here. So we go through the same arguments in terms of finding the flux through this surface S. Everything here is the same except we're inside, so we'll have again the area of that particular sphere times the E field as a function of r. This is the magnitude. All we've done is treat this as a vector field which has this property, that it has the radial dependence of the magnitude and is in the r hat direction. And if you recall, I stated that the symmetry arguments will give us this result here. If we look at the right-hand side, so just to repeat, this is the left-hand side. The right-hand side is the Q enclosed by a surface S divided by epsilon 0. So here's our rho. It's constant for all r less than a, so we're inside the sphere. This will be times the volume of the sphere of radius r. All will be divided by epsilon 0. So up here is the charge enclosed by the sphere of radius r inside. So if we take the volume of a sphere of radius r, which is right here, multiply by the charge density, which we formed by taking Q divided by the total volume of the sphere. This is the total volume. This is the volume of the sphere inside at radius r. Working this out then, we'll have for the right-hand side this expression here, where we have an r cubed dependence here, a cubed over here, times q. So now we take the left-hand side, which is here, and the right-hand side, which is here, and we solve for the field as a function of r, the magnitude. And so putting that in, we end up with this expression here. So notice you had an r cubed here and an r squared, so we end up with a r dependence which is just linear in r. So the E field inside now is given by this expression, and so as long as r is less than a, we have this for the E field. So let's just plot the magnitudes. I've written the expressions for the vector field, but this would be the magnitude, this would be the magnitude. For r less than a, we have this linear expression here. For r greater than a, we have this 1 over r squared dependence here. And notice that if you set r equal to a, it's actually continuous. We have the same value on both sides of r equal a. So that's the electric field for a uniform charge density in a spherical geometry as a function of r. Another related problem is just a spherical shell. Let's say we have a surface charge density, which this should be a sigma, like that, and a total charge q. We'll quickly go through the symmetry arguments. We do the same thing as we did before. We form a ring such that it is in the surface. Here's the surface of the spherical shell. So this ring is in the surface. We use the same arguments as before. The field at P, due to this ring, dE, is in the z direction, which is in the r direction, and only depends on z. So we have both the direction of dE and the functional dependence of the dE. If we use lots of rings, so in other words, if we were to integrate over all these rings, each one oriented just like the other one, so it's always perpendicular to the z-axis here, they will all satisfy this up here, that it's in the z direction, which is r hat, so it's in the r hat direction, and it only depends on r. That means then that we end up with the same form that we had for the uniform charge, namely that E is equal to a scalar function of r only in the r hat direction. And that's before we wrote this down. It was for both inside and out, and that is true here. But we analyzed this for a point outside, but we could have done the same thing for a point inside. So let's go inside first. Here's our E field, so I'm just repeating that. And here's our surface, our Gaussian surface, we draw inside the sphere. So we go through the same arguments as before to find the flux. And the flux is given by the flux integral here. So for this particular surface, we go through our E field argument, our area argument, so that when we take the dot product of this, we end up with E sub r on that surface S1. So r tells us that this is a constant if we keep r constant, which is the case for a sphere, and then times the ds1. This is a scalar now, scalar times a scalar. Because this is constant on that surface, we can bring it outside like we did before. Here is the area of this sphere. It's the area of the sphere S1, and that's what we mean by the area of a sphere of radius r. So our left-hand side is just like we had before, E of r only times 4 pi r squared, which is the area of S1. Now let's do the right-hand side. Here's where we end up getting our 0, because the Q enclosed, there's no charge inside, and so that will be equal to 0. Therefore, we can write down this side here is equal to 0. As long as r is less than a, we have the E field is equal to 0, so the vector capital E of r is equal to 0. You have to do all of the above to conclude that E is 0 inside. Why? Because we can't do this integral without the symmetry arguments. And in order to write down an expression for this quantity here, we have to have it in this form. Once we have it in this form, then we can evaluate what the charge inside is, and we chose the sphere in order to get this argument here. So that was in the case of a sphere of radius r. This, of course, is the right-hand side, so we end up with these being 0 and the vector form being 0. Okay, so outside we do the same thing that we did before. We take a radius greater than r. This is our E field as we had for the spherical symmetry problem. And so we write down our flux. There is no change here because of the symmetry. And so we end up with the flux integral being the scalar E of r times 4 pi r squared. So if you go through the same arguments that we did before, it holds for this surface here, and this is our result. So that's the left-hand side. Well, the right-hand side, which is the Q enclosed by S2, is the total charge on the sphere. So the right-hand side then is just Q over epsilon naught. So equating the left-hand side with the right-hand side, which is for r greater than a, we have the magnitude of the E field is just Q over epsilon 0 4 pi r squared. So we just brought this over on the right-hand side. And so that, in terms of K, is KQ over r squared. We end up then with the point charge expression for the E field. If we're outside of this spherical charge distribution, we'll end up getting the behavior of a point charge. One more time, you have to do what we did above in order to continue and find E outside. You have to have the symmetry arguments, which gave us this up here. You have to evaluate the flux integral, which is right here, which gave us the magnitude of the field times the area. From there on, after you get the right-hand side, you can find the E field. If we took these two charge distributions, we had rho of r being constant, we have rho of r being this shell, which by the way could be represented by a delta function in the r direction. If we're outside and we have any spherical charge distribution, it doesn't have to be this one, it doesn't have to be constant, we could have any spherical charge distribution. If we're outside, it will look like a point charge, where the point charge is simply the total charge of that charge distribution. But it has to terminate in order to say that it looks like a point charge. Let's plot this function. Here's what it looks like. It's 0 all the way up to a, and then it jumps up to the 1 over r squared values, and so that's this one right here. So I put the vector forms here, but realize what we're plotting is this magnitude function for here, and of course the 0 here. So this is the actual axis then is the magnitude of E versus r. So this is r, and this is the magnitude of E right here. Well, let's take a look at a problem that has cylindrical symmetry. So we're going to look at the E field due to a infinite line charge with linear charge density. We'll call that lambda. So here's our line charge along the z-axis. We're going to pick a point P here and let perpendicular distance from some origin be S, and ask what is the E field at the point P in terms of symmetry. So what we want to show is that the magnitude of E is just a function of S, and we want this to be in the radial direction S hat. So this means there's no Z or phi components, where phi is related to the rotation angle about the Z-axis. The argument for the direction of E is very similar to what we did before for a finite line charge. We took charges, dq's, on equidistant positions along the line from the origin and found the differentials of E fields due to those charges, so dE1, dE2. We argued that the components that were normal to the z-axis canceled each other, and so all we were left with was the dE in the z direction. I've changed the variables here, so now we have z here, and so this would be s along this direction here. But the important thing is that the E field is in the direction normal to the line charge. Just restating that for the direction of E, we use the same argument as the direct calculation of E for a finite line charge. We selected these dq's, and in this case it would be lambda dz, symmetric to the OP axis at plus or minus z. So that's these two elements here. And then we showed that the sum of these two differential vectors is in the s direction because the other components cancel. Well, this is true for all values of z. In other words, if we come way over here and we come way over here, we still have that symmetry, and so therefore we conclude that the E field at the position P is in the s direction, and that's true for an infinite line charge as well as for a finite one. So we'll continue with the symmetry arguments by asking about the dependence on z and the angle phi, which is the rotation about the z-axis. So the first thing is we'll translate the origin and p, so we'll just take this whole structure here and translate it along the z-axis back and forth. Because this is an infinite charge, we'll never see the ends of the wire, so nothing is changing in terms of the environment. So we'll see no change, so therefore the magnitude of E has no z dependence. Well, the same is true about rotating about the z-axis, which is changing the phi angle. We can rotate this in any fashion we want, and we'll still be seeing this line charge unchanged. So the result then is no change, and so E has no phi dependence. That only leaves s, and so the magnitude of E depends on s only. So as a result then, we combine these two results into the following, that the magnitude is a function of s only and is in the s hat direction. So now we're ready to introduce a Gaussian surface and use this. Okay, so we've got this combined result here. So we choose a Gaussian surface, this cylinder, that will be of radius s, so therefore P is on that surface, and is of length L. Everything is symmetric to the z-axis. The flux through this cylinder, by Gauss's law, is equal to the Q enclosed over epsilon naught. Let's look at the flux. E is always normal to the line charge, so therefore the ends of surface S have no contribution to the flux times area. On the other hand, when you look at the walls of the cylinder, because we have this equation here, the E will be normal to the walls of this cylinder. So we can go through arguments similar to the sphere. We can write down what ds is, and that's going to be this element of area times s hat. We have our E, which is given by this value here, and so we write the dot product, and so again we have a unit vector dotted into itself, which is 1, and so we're left then with the magnitude of s on that surface, which is constant on that surface, times the magnitude of the surface element. Putting in the values here then, we'll have E of s, E as a function of s, times the integral of ds. So all we've done is taken this quantity here and we're integrating it over the surface, and so that's what we end up with. This comes out of the integral, so here's E sub s outside, and we're left with the area of the surface S. Here it is again, here's E sub s, and this is the area of a cylinder of radius little s and the length L. The left hand side then is equal to the integral, and so that'll just be the E sub s times the area. The area is 2 pi s times L. So it's the distance around the cylinder, which is 2 pi s, times the length of the cylinder. So that's the left hand side. So I repeat that here. Here's the left hand side. Here's our cylinder. So now we do the right hand side. So all we have to find is the charge in this portion of the line. And so that will just be the length of the line times the charge density. We divide that by epsilon 0 to get the complete right hand side. Setting then the left hand side equal to the right hand side, solving for E sub s. This is the magnitude. We end up with a lambda over 2 pi epsilon 0 s. We've divided by this to get that. By the way, you see the L's cancel. And then we get, introducing 1 over 4 pi epsilon naught, we get this expression for the magnitude. So putting back the direction s hat, we have then the vector equation for the E field is equal to this quantity here, which would be the 1 over s dependence times s hat. And I just want to point out that if you go back to the finite line charge and take the E field that we found there, which we represented, by the way, in the z direction, in the normal direction, and then just let the length of the line go to infinity, you get exactly the same dependence here. This is a very useful equation for the E field due to a line charge. Well, I want to go back to spherical symmetry because I mentioned this rho of r which extends to infinity. The question is, can we find the E field as a function of r by taking advantage of our symmetry arguments? And this is true because this is a spherically symmetric charge density. It's a function of r only. This is a plot of rho sub r as a function of r. And this is not 0. It keeps going, but it's very, very small. This, by the way, is half of what is called a Gaussian distribution function. Well, we use the same argument as before to obtain the left-hand side. And so we again build a Gaussian surface that's spherical at radius r. And I'm using the same picture, but this distribution that we showed before, which was uniform, is actually this one. So it extends out beyond the edge of this diagram. We want to get the flux through that surface, and so we look at the left-hand side. We look at this for this surface S. We use our symmetry arguments to get the expression here. Everything stays the same, and we end up with the same expression for E sub r times the area of that sphere of radius r. So the left-hand side looks exactly as we obtained before when we have this spherical symmetry. If we now look at the right-hand side, so here's our results here. The right-hand side is the Q enclosed over epsilon naught. That is equal to 1 over epsilon naught times the charge density, which is a function of r, integrated over the volume of that sphere. Well, if you look at the integral to obtain that, this is in fact the volume integral here, then what we have is an integral over r where I've already integrated over theta and phi. And so when we do that, we get this expression here where here is our rho of r, and then we have 4 pi r squared dr, and that will give us the total charge inside of that sphere. Separating this out, this is this integral here. Being lazy, I threw that into Mathematica and got this complicated function here. Can that be simplified? Well, probably, but I just left it as is. So then we can go back to equating the right-hand side to the left-hand side. And I've already taken the 4 pi r squared away from this side and put it down here. This quantity here, this function, is in fact E as a function of r for this Gaussian function. So let's plot that, and you can see here this is the E of r as a function of r, and it's this messy function here that you see here. So it starts at 0, and it goes up and reaches a maximum, and then comes down like this, and this is not 1 over r squared. This is not linear. The curvature that you see here and the functional dependence that you see here is more complicated because of this more complicated charge density. Next time we're going to move on to the electrostatic potential.